All right. So limits day 3. What we know. So as we sort of move through a unit, the what we know list is going to get longer and longer and longer. And the what's new sometimes builds on what we learned before. And in today's case, it actually ties in really closely to things you learned in either pre-calculus, Math 141, or if you were part of the STEM core group, we did that in Math 116, okay? So things that we know or that we have covered in the first week of class. We know what a limit is. We can find it graphically. We also went over examples on how we find it without a graph, and that includes factoring and radicals and complex fractions and trigonometry. And we also took a look at this idea of continuity. So how does something being continuous relate to limits? And so what's new in this section is how do limits apply to vertical asymptotes? How do limits apply to end behavior? And how do we see these limits graphically and numerically, okay? And so there is, if you check out your classroom on Desmos, there is an activity that is called Rational Functions Review. Now, based on the feedback from earlier, I'm going to leave that for you to do on your own time. So you can, if you took Math 116 with me, you can also refer back to, I think it was 3.7 part 2, okay? But the rational functions review activity on Desmos should give a nice summary of some of these things that we're going to talk about today, in case they were things that sort of weren't things that you remembered right off the bat, okay? So I'll leave that for you to do. It is already in your Desmos classroom, okay? All right, so let's get right into this. Limits and vertical asymptotes. That's where we're going to start today. And what we're going to start with is things that I think most people feel comfortable with, which is looking at a graph and tying that to limit notation, okay? So let's start with this first graph here. Vertical asymptote, where is it? Ooh, I'm going to ask you to be more specific. Ah, there we go, there we go. Okay, so at x equals 0, there is a vertical asymptote, okay? So I'm going to go ahead and highlight that right here, whoops. And we can say that we have a vertical asymptote at x equals 0, okay? All right, now, when we look at asymptotes, we like to see what's happening from the left and what's happening from the right, okay? So if I wanted to write what is the left-hand limit, okay, using notation, I would write that as the limit as x approaches 0. Now, how would I say from the left? Like, what do I need to include here in order to say from the left? Yeah, we need a superscript minus sign. Very good. Okay, so the limit as x approaches 0 from the left of our function equals. Okay, now as we get closer to the left side of this vertical asymptote, what does the y value of the function get really close to? I love that. Okay, yes, negative infinity, right? And if we look here, we can see that this graph goes down, okay? And so the y value it's getting close to is negative infinity, okay? What about the right-hand limit? What can I modify about my previous statement to make it have, say, right-hand limit? Yeah, we need a little plus, right? That plus means right-hand limit. So this limit, the right-hand limit of this function. And what y value is this function getting close to as we come from the right-hand side of 0? Yeah, let's check that out. From the right-hand side, sure does look like it's going way up, right? And so we can say it goes to positive infinity, okay? Does that make sense so far to people? We're still using the same idea of looking at a picture and zooming in a particular part, but now instead of getting like a number out, we can say it's going to positive infinity or negative infinity. Ethan, what is your question?
Looks like I accidentally raised my hand from a keyboard
okay.
shortcut. Sorry.
Super awkward. I'm just kidding. It's not awkward at all. That's fine. Okay. Okay. So let's take a look at this second graph now. Where is the vertical asymptote? X equals -4, x equals 1. Okay. Trick question. This function has no vertical asymptotes. Does anybody know what the equation for this function could be, by the way? Yeah, it's just like a cubic function. So this might be some sort of like y equals x cubed situation, okay? Plus some other things, right? Okay, but sometimes we don't have a vertical asymptote. And I think that's really important to remember, because when we're doing all these problems, we sort of focus on the weird cases, like this first one we looked at, that we forget that some cases are totally normal and they totally don't have a vertical asymptote, and that's okay. Right, so this one doesn't have a vertical asymptote, so we don't really have anything to describe in terms of what's happening around a vertical asymptote, okay? Does anyone happen to remember what the equation for the first one is here that we looked at, that first picture? Y equals 1 over x. Yeah, okay, okay. Someone tell me, this y equals 1 over x. What is the degree on the top? I agree the function overall is odd, but the numerator is 1. What's the degree of 1? Okay, so the degree of 1 is actually 0, because it's really x to the 0, okay? So it's not the power of the number, it's the power of the variable, okay? So the power of the top is 0. What's the power or degree on the bottom? That one is 1, okay? Which one's bigger, degree on the top or degree on the bottom? Degree on the bottom, okay. What about this second picture? What's the degree of that second picture? Third degree, okay. Yeah, it's like x cubed plus some other things. I don't know what those other things are, but it's that cubic part that gives it that general shape. Okay, cool. All right. Last one here. Let's talk about this particular case. So where is there a vertical asymptote? Be more specific. Okay, we want to really get into this notation here. Okay, so x equals +1 or x equals -1. Good. So if I highlight that here, I see that I have 1 like right here, and then I have another vertical asymptote like right here. Okay. And so let's take a look at this one first, at x equals -1, and then we'll take a look at x equals 1, okay? So we'll say this one is for x equals -1, and the second box will be for x is +1, okay? And we're just gonna ask ourselves the same questions. What's the limit as x approaches -1 minus of our function? And what's the limit as x approaches -1 plus of f of x? Okay, so let's start with the negative, x equals -1 asymptote first. Tell me about the left-hand behavior there. From the left side of -1, what is the function approaching? Yeah, that's definitely going down to -infinity. Okay. And what about when we approach that vertical asymptote from the right-hand side? What y value does that get really close to? Right, so this, like last time, is going up to +infinity, okay? Now let's look at the other vertical asymptote. Okay, so we've got the little negative sign to mean coming from the left and a little minus sign to mean coming from the right. What is the left-hand limit as we approach 1? The left-hand limit as we approach 1. I would say that it's not -infinity. +infinity, right? Because this side that is left of that is going up. Good, so we need a +infinity. And now I would say your answer would be correct for the right-hand limit, that when we approach x equals 1 from the right, it's going down to -infinity, okay? Now, what is this? Okay, why is that does not exist? I would agree that this overall limit does not exist, but how come? Exactly, Jorge. The left-hand limit does not equal the right-hand limit. And same thing, Megan, because the limits from both sides are not equal, okay? So even though we have answers that look like infinity and -infinity, if they don't match, then the limit does not exist, okay? Now we could say the same thing for the limit as you approach a +1, that limit does not exist, okay? So we really want to be careful here. Some rules are exactly the same, which is if the left side doesn't meet the right side, we're out of luck. The limit does not exist, okay? All right, so let me zoom back in here for a moment. Are there any questions on finding limits from the picture? Like, how are we getting +infinity? How are we getting -infinity? Are we okay doing that from a picture? Okay. If we're okay doing things from the picture, I think that's a good place to be, okay? If you're still confused about the picture part, it's really, really important that you come to office hours or you go to tutoring so that we understand how to find these values from the picture, okay? So that leaves us with this question: how do we do it when we don't have a picture? And the answer is not plug it into Desmos, I get a picture, I get an answer. Okay, I mean, it could be, but we also want to make sure we know. I know, so sad, right? We also want to know how these things actually come to be. So let's start with example number 1 here. Okay, so example number 1. So what I'm going to say is we need to find whether or not there are vertical asymptotes. And my guess is that there are, because I have a fraction here. I have a rational function. So I have some x's on the bottom, which means that at some value of x, we're going to get a vertical asymptote, or it's going to be undefined because I'm going to be dividing by 0. So in order to find that, I'm going to say, let's go ahead and factor. Okay, so we factor that numerator and we should get something like this. Okay. And we factor the denominator. Okay. So you factor. Does this function have any holes? No. Okay. There are no holes. And our reasoning for that would be something like there are no factors that are in common between the numerator and the denominator. So we could say there are no holes, but how many vertical asymptotes? There are 2 vertical asymptotes. Okay. One is going to be at x equals -2, and the other one is going to be at x equals 1. The review activity does go over that a little bit more in detail. So if you want to check out that activity, that should clarify a little bit more of this, okay? So let's start with x equals -2. Okay. And what we want to find is what is happening on the left of that and what is happening on the right of that. Okay. So in other words, is it going up or is it going down? Is it going up to positive infinity or is it going down to negative infinity? Okay. So when we think about vertical asymptotes and we're looking for limits, our answer should be positive infinity or negative infinity. Okay, because just like the graphs we saw, the graphs are going either really, really far up or the graphs are going really, really far down. Okay, if you get a number out, you probably did some computations incorrectly. Okay, but let's start with the left-hand side limit. So the left-hand side, that is the limit as x approaches -2 from the left of this function. Okay. So here's what we're going to do. We're going to sort of think about using numbers to help us out. Okay. So I want you guys to pick a number that is really close to -2, but is a tiny bit to the left of -2. Okay. So it looks like Aylin has said -2.1. We agree that -2.1 is to the left of -2. Yes, no, yes, okay. So I think that's a good number to pick. And what we're gonna do is everywhere we see an X, we're gonna replace it with a -2.1. But we don't need our calculators. I promise we don't need our calculator. Okay, so we're just going to write it in with the substitution. So 2 times negative 2.1 minus 1, negative 2.1 plus 3, negative 2.1 minus 1, negative 2.1 plus 2. And now everywhere that I saw the x, I plugged in that number. Okay, that's all I did. Now, the reason why we don't need a calculator is because I don't care what the number is going to be. I care whether it's positive or negative, like the whole equation. Because if the whole equation is positive, then what it means is your graph is going to be going up really high, which means that your graph is going to have a limit of positive infinity. But if we get a negative number out, it means that our graph is going down to negative infinity. Okay? So I don't care what the number is, I just care whether it's positive or negative. Okay? So let's take each of these parentheses piece by piece, and let's figure out whether it's positive or negative. So let's start with this one right here. Negative 2.1 times 2 minus 1. Is that positive or negative? That is negative. Good. Negative 2.1 plus 3. Positive or negative? Good. Let's move to the denominator. Negative 2.1 minus 1. Positive or negative? Good. And let's move to the last parentheses, negative 2.1 plus 2, positive or negative? Good, 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 good. Okay, now, you tell me, based off of what you know about multiplication and division of positive and negative numbers, is this overall going to be positive or negative? Yeah, it's going to be negative, right? But that doesn't mean that our answer is negative, like just a negative sign, right? Our answer is actually negative infinity. So we need to include that part in there because we're not just finding out whether it's a positive value or a negative value, but we're using this to approximate what happens in a picture kind of like this, where that graph goes really far down to like the left of a vertical asymptote. Okay, so it's important that you don't just write negative as your answer, but that you have negative infinity to show whoever's looking at your work that you understand that because it's a vertical asymptote, you're approaching either positive or negative infinity. Does that make sense? Okay, so the bad news is every vertical asymptote has two sides, right? So we've done the left-hand side. Now we must do the right-hand side, okay? So we're gonna set up a similar structure where we're gonna take the limit as x approaches -2, but this time from the right. And we're gonna copy down our equation, but this time, while I'm writing this, can someone pick a number that is really close to -2, but a little bit bigger? Okay, so -1.9 sounds perfect. Let's go ahead and everywhere we see, oops, I think I used orange. Everywhere we see the x's, we're gonna put in that 2 times -1.9. Okay. And same thing as before, all I did was substitute in. And we don't want to get nervous and grab a calculator, but we want to think, What do we know about the signs of things? Okay. So double check me on this, but I think this is what we get. Negative, positive, negative, positive. Okay, I'll give you a moment to double check my work. Did you also get negative, positive, negative, positive? Now again, I'm not typing things into the calculator, right? I don't, and the reason why is not just because like a calculator is bad or whatever, it's not bad, but I think we don't care about the number. The number doesn't actually matter, but what matters is the sign, okay? And so this time, now that we've got negative, positive, using what we know about multiplication and division of positive and negative numbers, we should get that the sign overall is positive. But we don't want to just leave that as an answer. We want to say positive infinity. Okay? Does this structure make sense to people? How we sort of factored it, we plugged in some numbers, and then we were able to think about whether it was approaching positive infinity and going up or approaching negative infinity and going down. See a few yeses. I also know there are people I've not heard from, so. Okay. So I think Ethan said that really well. Is our only decisions are that is the graph going up or is it going down by that vertical asymptote? Those are our only two options. And so to decide whether it's going up or down, we pick a number that's like really close to the vertical asymptote, and we just see, is it going up or is it going down? Because that means like every other point we choose will also follow that same pattern. Okay, so I picked negative, or you folks picked negative 2.1 for the first one, the left-hand limit. But if I picked negative 2.000001, I would still get a negative number. It would still mean that the vertical asymptote goes down, or the graph goes down to the left of that vertical asymptote. Thea, does that clear things up, or is that even more confusing? Okay, so let's sort of like think about this as the picture of the graph real quick. So if I wanted to sketch a graph of f of x, I know from earlier, right, we said that this has no holes but two vertical asymptotes. So where are those vertical asymptotes? Well, one is at -2 and one is at 1. So here's one, here's the other. Right? And that's stuff that we learned in pre-calculus. And so the question now is, well, how do I know whether the graph goes up or down on the sides of the asymptote? So what I can tell from this left-hand limit here is that when I go to x equals -2, on the left-hand side of that, my function is going to be going down. That's what this minus infinity means. So then we said, well, what does it look like on the right-hand side? We picked a number to the right, we plugged it in, we found that it gets close to positive infinity. So I know that graph looks something like that. I don't know what the rest of the graph looks like, but I know those two pieces of the graph. Okay. So if you remember way back when we did this in 116, I was like, oh, don't worry about this part. Like there is a way to figure it out. I think I might have even shown you guys one time, but I was like, we'll get to it in calculus. And so here we are, like we're not necessarily plotting points, but we're plotting patterns that are happening on a specific graph, okay? Should we try the same thing with both sides of x equals 1 and see how that goes? Okay, so we can see what's happening on the other vertical asymptote. Okay, so let's now try x equals 1. Okay, for the left-hand limit, I'm going to say the limit as x approaches 1 from the left, so a minus sign of the function. Okay. And now, Thea, I'm going to put you on the spot. If you could tell me a number that is a little bit smaller than 1. Okay, so pick a number that is a little bit smaller than 1. And we're going to put that number in everywhere we see an x. 1. A number that's smaller than 1. Yeah, 0.9, right? Okay, so everywhere I see the x, I'm going to type or write in 0.9. You're fine. Okay, so we picked that number, 0.9, 0.9, 0.9, 0.9, and now our only job is to say, hey, are things gonna be positive or negative? What's happening? Okay. So in this first one, 2 times 0.9 minus 1, that's gonna be positive. 0.9 plus 3 is gonna be positive, and then on the bottom I get negative and positive. Okay. Does that part of the process make sense? Okay. And now we know that a positive number divided by a negative number is going to be negative. But because we picked a number that was so close to 1 and we got negative, it means that when I go back to my graph at x equals 1, on the left-hand side of it, the graph will be going down. So I can already start to sketch this graph if I wanted. I know that this middle part maybe looks something like this. And I don't know exactly where it crosses the x and the y axis, and we could find that out, but it's not really important to this particular lesson. We're just looking at like what's happening on the sides of the vertical asymptote. So does that kind of clear things up a little bit more? Okay. So just to finish this one, if we were to do the right-hand limit, okay, we want to sort of finish like what the other side of the picture looks like. And everywhere we see an x, we're going to pick a number that is a little bit bigger than 1. So let's say 1.1. Okay. And I think we'll see that this ends up being positive, which means that the other side of the asymptote is going up like this. Okay. Now, I don't know exactly what things look like, but my guess is if you threw this on Desmos, it might look something like this. Okay. So even though this is only one example, I think it shows us a lot of the process that we're doing here, which is we got to figure out where the asymptotes are. So like before we do anything else, we have to figure out the vertical asymptote location. And then using what we know about vertical asymptotes, we know the graph either goes up or it goes down. Those are our only options. And instead of saying, I'm just going to guess one or the other, it's a 50-50 chance, right? We're going to pick some numbers and use those numbers as samples to show us which direction the graph is trending in, okay? And so that's sort of the gist of what we do with limits as we're around vertical asymptotes, okay? So for the sake of time, I'm not going to do example 2 but in class, but I will write it out before I post my notes. So you'll have another worked out example for you to look at to help with that quiz and to prepare for the exam, okay? So let's shift gears a little bit and look at limits, but this time not looking at the vertical asymptotes, but the end behavior, like what is happening at the ends of our graph, okay? And so let's take a look at this first picture here. Can someone tell me, is there a horizontal asymptote? And if so, where is it located? Okay, so I see one yes, that there is a horizontal asymptote at y equals 0. And if we drew that in, it would kind of look like that, right? And we could say that we have a horizontal asymptote at y equals 0, okay? Now, I want to know, similar to when we did the trig stuff at the beginning of class, what is the limit as x approaches negative infinity of this function? Okay. And then separately, I want to know what the limit as x approaches positive infinity of this function is. All right. So as we go all the way to the left, we trace all the way out here. Yeah, we're going to get close to a y value of 0. Absolutely. Okay. So this we call left end behavior. Okay. And so that's just saying what happens if you go all the way to the left? What y value does the graph approach? Similarly, I could say, what is the right end behavior? Okay. And that would mean I'm saying, what happens when we go all the way to positive infinity, right? And in this case, they both approach 0. And check this out. This is 0. The right end behavior is 0. The left end behavior is 0. But also, my horizontal asymptote is y equals 0. That's not a coincidence. So when you were studying in pre-calc about horizontal asymptotes, you should be able to translate that same idea, right? Like we have this function, it has a horizontal asymptote, but that horizontal asymptote is the same thing as saying end behavior, okay? So that's really something we want to connect in our heads, that horizontal asymptote is actually one type of end behavior. Now, earlier with this graph, we said that the equation was 1 over x. And we said that the degree on the top was 0 and the degree on the bottom was 1. And therefore, the degree on the bottom was bigger. So that might be a rule that you remember from pre-calc, that if the degree of the numerator is smaller than the degree of the denominator, then you have a horizontal asymptote at y equals 0. Okay, so this is probably a rule that you learned at some point in your pre-calc class. All right, let's take a look at this second graph now. If I say the limit as x approaches negative infinity of this graph, what would you say that left end behavior is? Okay, how do you know that? I agree, negative infinity. And we can find that just by saying, well, if I keep tracing, that function keeps going down, right? So that left end behavior is negative infinity. Now, maybe in pre-calc, you talked about it in terms of up or down, right? And so we're just graduating a little bit here and saying negative infinity instead of down, okay? What about the limit as x approaches infinity? Or in other words, the right end behavior. What is the right end behavior here? Yeah, exactly. Positive infinity. Good, good, good. Okay. Now, earlier, we said that this equation was something like x cubed plus a bunch of stuff, okay? And so the degree of this was 3. But in this case, if we think about this as a fraction, it's really something over 1, okay? We can make anything into a fraction by putting it over 1, but the degree of the numerator is 3, which is actually larger than the degree of the denominator, which means that there is no horizontal asymptote. Okay, so that might also be a rule that you learned in pre-calc. Okay. So thinking about comparing the degrees tells you about end behavior. It tells you about whether it has a specific kind of end behavior like horizontal asymptotes, but it tells you about, in general, the end behavior as well. Okay. All right. Last but not least, let's take a look at this one. If I say the limit as x approaches negative infinity, and if I ask you also for the right end behavior, I'll give you a moment to look at that graph. But what do we think those two limits are as we go to infinity and negative infinity? Okay, I see 2. Any other thoughts? Do we agree with 2? Do we disagree? Okay, yeah, I would agree that this one goes, when we go this way, it gets to a y value of 2, or it gets really close to it. And then if we trace the other way, the right end behavior, we also get to 2. Now, even if you don't remember this from pre-calculus, I bet you can guess based off of what we've already written. What do we think is true about the degrees of the numerator and the denominator? Yeah, exactly. So if you remember these rules from pre-calc, you might remember that the degree of the numerator is equal to the degree of the denominator. Then you have a horizontal asymptote at y equals, and you have to divide coefficients. All right, so you have your leading coefficient on the top and your leading coefficient on the bottom, and you divide those. And in this particular graph, when you divided them, you got 2, which is why that end behavior is also 2. Now, folks typically really like these rules because it's very quick and easy, especially in like an open note exam. I think that's absolutely fine. I think it's also important to think about these rules. Like I've seen them definitely come up again and be useful when you get into like discrete math. It comes up a little bit. LC stands for leading coefficient. Okay. Okay. Now I think let's do this. Let's just take a look at these 3 examples right here, okay? Think about the rules that we just talked about, and then see if you can figure out what the end behavior is, meaning what is the limit as x approaches infinity or negative infinity for each of these graphs. Okay, so let's take maybe another minute or so of think time and thinking about the rules that we just reminded ourselves about and how they might apply to the different cases. Like, how do we know if something has a degree that's bigger on the top or the bottom, right? I think it's good practice to think about that. Maybe in about another minute or so, we'll check over our answers for this. All right. So let's take a look at example 3 here. Do we think in example 3 that the degrees on the top is bigger, equal to, or less than the degree on the bottom? Okay, they are indeed equal, right? And so let's highlight the terms that really help us find that. 2x to the 4th. And I'm going to say, this is so important. I'm going to zoom in even more. Negative 5x to the 4th. Okay. So 2x to the 4th means the top has a degree of 4. Negative 5x to the 4th means the bottom also has a degree of 4. So if the degrees are equal, then to find these limits, we just take those coefficients and we divide them. So you could write 2 over -5. You could say -2/5. You could even say -2 over 5. Those would all be equal. Okay. And because it's a horizontal asymptote, it is exactly same on the other end. Okay. So does that make sense how we're able to look at the degrees and then use that to determine what the end behavior is? Remember, horizontal asymptotes are just another name for end behavior. All right, let's take a look at example 4 here. Degree on the top is greater than, equal to, or less than the degree on the bottom. Greater than, good, because we have an x to the 6th, which means 6th degree on the top, and -5x to the 3rd, which means 3rd degree on the bottom. Okay, good. Real quick, so it will always be the same on both sides if it is a horizontal asymptote. Almost, Megan, if there's only one horizontal asymptote, then yes, and that is most of the cases that we look at. Okay, I think there's a logistic function where the logistic function looks something like this. That one actually has 2 horizontal asymptotes, or like the inverse tangent graph only has 2. And so then you would need to see what's happening on either end. Okay, but those are a little bit more rare. They don't come up quite as often. Okay, I'm not trying to be super tricky on an exam or anything. Okay, so we'll be sticking to like, there's like one horizontal asymptote, you have to find it. Okay, but in this case, if I were to just think about these degrees, I could almost say this. And what does that reduce to if I were to reduce? X to the 6th over -5x to the 3rd. Yeah, like a negative x cubed over 5. Okay. Now the important part here is this negative and the x cubed. One of the parent functions that I think is really helpful to know is the cubic one looks like this. But so this is like an x cubed, but a negative x cubed looks something like this. Okay. If you know that, these questions aren't hard. Negative x cubed on the left-hand side, that goes up. Negative x cubed on the right-hand side goes down. Okay, so those parent functions that those of us who were in 116 together, we spent a lot of time on those parent functions. If you still remember those, it's such an easy shortcut to use during this section. Okay, because if you know what the graph looks like, you have a picture. You have a picture in your head, right? And you have that picture, then you can answer the questions about limits. All right, I think we can just squeeze this problem right in. This last one here, degree on the top is a 2. Degree on the bottom is a 4. The degree on the top is smaller than the degree on the bottom. And so what does that mean about our horizontal asymptote, other than it has 1? Yeah, that horizontal asymptote is specifically at 0. And so we just fancy that up. We say the limit as x approaches negative infinity is 0. The limit as x approaches infinity is 0. Okay, so it's new notation with some old concepts, right? Now, there is a summary here in case you want to refer to that. That summary is probably helpful in terms of figuring out the questions. But that is all we have for today. I know we are just a minute over, so I appreciate those of you who stayed on.